Okay, Physics 11H, here's Worksheet 3.1.2. I'm just going to do a few questions off this, half of them, but I'll write up the solutions for the whole thing so you can take a look and ask me any questions you might have. Again, I know this is probably a little bit hard to see, but maybe look at the actual solutions online as you watch this video. I'm going to post them as soon as I'm done. I'm going to scan it, get these posted for you, okay? I guess I probably need to post the Regents sheets too for those that weren't there on that fateful day, the last day of school. 5 kilogram block is sliding east at 2.5 meters per second. When it collides with a 3 kilogram block at rest, the two blocks collide with no sticking, and the 5 kilogram block comes to a stop after the collision. All right, so we got a picture right here. I think we're gonna write. I'm going to draw it down here first, actually. So, sliding east at 2.5 meters per second. This one's V is 0. Afterwards, this one's V is 0, and this one goes moving away. Spoiler alert, it's going to be faster. It's less mass, so when this one transfers its momentum, this one loses all of its momentum into this littler one. So the littler one's got to slide away faster. I have really great stuff to show you this at school, but, it doesn't work. I got to go check FET, see if they have any collision stuff yet. I don't think they do. But anyway, so now we do conservation of momentum. P before the collision equals P after. I'm writing a little bit small here. I apologize. Oh, you know what? Let me give you guys some extra light here. What am I doing? I don't have my lights on. There we go. P before equals P after. So before the collision, we have 5.0 kilograms times, I'm going to put positive on here just to be careful, just to make sure I'm doing good momentum practice. All right. This one's momentum before is MV is 0, so that's just plus 0. And then after the collision, the incoming blocks is 0 plus 3.0 kilograms times V final. I'm just calling this V final here. That's our final velocity we're looking for. Again, I'm sorry this is a little small. Follow along on the PDF. I could try zooming in, I suppose, and slide the paper around, but I'm afraid I'd lose. Let's see. Is that better? We'll see how that goes. I got to refocus, though. It's probably a little pixelated, but oh well. All right, maybe that'll be better. All right, but now I got to move the paper around, so that's a bit annoying. There we go. So, speed of the 3 kilogram block after the collision. So we've got this MV plus MV. 5 times 2.5 is 12.5. I'm going to drop the units right now. We don't need them. 3 VF. VF is 12.5 over 3, which is 4.2 meters per second. And it came out positive. So therefore the velocity of this block is positive. Okay? All right. A little pixelated, but we'll deal with it. Number 3 I'm going to do now. Get a notification here. Oh, don't want to zoom in anymore. That was a mistake. Darn thing. All right, let me just zoom back out a little bit. All right. Hey, that's not too bad, really, all things considered. 0.25 kilogram lump of putty is thrown to the east at 7 meters per second. The putty collides with a 1.5 kilogram block that is moving west at 0.5 meters per second. The putty and the block stick together after the collision. Determine the velocity of the putty and the block after the collision. I'm going to do the drawing before again, okay? So the putty mass is 0.25 kg, moving with a velocity of 7.0 meters per second. This one is mass is already labeled. It's moving at a speed of 0.5 meters per second, but I need to make it negative. I absolutely need to make that velocity negative. All right. After the collision, they stick together. They're essentially one big mass of a mass of 1.75 kilograms, and we want to find out what the velocity is. I'm not even going to draw it on there because it might be to the right, it might be negative. I don't know yet. Let's do the math. So just like we did on the previous problem, P before equals P after. I really should have zoomed in on that previous video, but oh well. P before equals P after. So before the collision, we've got 0.25 kilograms times positive 7 meters per second plus 1.5 kilograms times negative 0.5 meters per second. So we've got a lot of momentum before. And after the collision, it's going to be a total mass of 1.75 kilograms times the unknown final velocity. All right, hopefully everybody can see that all right. Notice, be careful here you don't make a double negative, right? I've got negative 0.5 already here. I already put in the negative sign on the velocity. Don't then put it again here, all right? So let's go ahead and plug and chug this, pound it out in the calculator here. All right, actually, let me move this over and make you see my calculator, see what I'm doing now. This is kind of nice, actually, this is zooming in stuff. All right, so 0.25 times 7 gives us 1.75. 1.5 times negative 0.5 gives us negative 0.75 equals 1.75 times VF. All right, so do this math first. 1.75 minus 0.75 is 1.0 equals 1.75 VF. Notice that this side came out positive, right? That matters. That matters. There's a positive on the answer here, right? That tells us which direction these are going to move off together. So 1 divided by 1.75 gives us, VF is right there. That was stupid what I drew right there. That was not good looking. I guess it's VF, but it looked terrible. So, you know, I don't have any white out at home, so we're just going to roll with that. VF equals 0.57 meters per second, and it did come out positive. That's very important. Cool. That's a fun question. That's a good one. So we see one where they bounce off of each other, right? We just got to be careful with our signs. They're all the same setup. P before equals P after, but then we just add up the MVs. Whatever was before has to equal what was afterwards. So they stick together, I make them one mass. If they bounce off each other, that's a little bit different. And pay attention. So now I'm just going to go to the back quick, do a couple here, multiple choice. A 0.05 kilogram bullet is fired from a 4 kilogram rifle, which is initially at rest. If the bullet leaves the rifle with a momentum of 20 kilogram meters per second, the rifle will have a recoil with a momentum of what? All right, so this is a classic problem, right? I draw like a musket. You know, we don't want it to be some sort of modern gun. You know, it makes people nervous. So it's just a musket. It's got this bullet sitting inside of it here, right? When you fire it, the bullet's going to leave. So this is before. So afterwards, right? You got your musket. Terrible, terrible drawing. Not one of my finer ones. The bullet now, the musket ball, is traveling at a high rate of speed. All right, it's got forward momentum. Turns out the gun has backwards momentum. I drew this vector way too big. Not good. That is equal and opposite, right? Because initially, P initial equals 0. P final must also equal 0 then, right? P before equals 0, P after must equal 0. So if we write P before equals P after, we have 0 equals the momentum of the bullet plus the momentum of the gun, right? So if the momentum of the bullet is 20, the gun must be negative 20. It's got to have the same magnitude to be able to cancel out the forward momentum of the bullet. So the heavier the bullet, the more the gun kicks. The faster the bullet, more the gun kicks, the more recoil there is. This is a interesting one you can look up on YouTube. Maybe I'll post a link to it in the topic, but it's the nuke cannon. All right, I usually show this video in class when we talk about this because it was actually developed during the Manhattan Project, essentially, well, the continuation of the Manhattan Project, to shoot a nuclear bomb with an artillery gun. And it's actually, they got the gun like mounted on a sled, and when it fires, the sled goes, and it's like, you know, there's a delay, and then all of a sudden nuke explosion in a beautiful desert background. It's really quite a striking video. I'll have to post a link to it. So the answer here is 3. The gun must have the same magnitude of a momentum going backwards as the bullet has going forward. And the last one I want to go over right now is number 8. A 1.2 kilogram block and a 1.8 kilogram block are initially at rest on a horizontal surface. When a compressed spring between the blocks is released, all right, so there are 2 blocks, frictionless. There's a spring between them. Afterwards, the spring is released, right, and they go flying away. So it's 1.2 kg, 1.8 kg, 1.2 kg, 1.8 kg. They're going to go in opposite directions no matter what. It's just like the gun. Whatever momentum one of them has going to the left, the other one will have to have going to the right. So it says the 1.8 kilogram moves with the speed of 2.0 meters per second. What speed does this block have? All right. So P before equals P after. So 0, everything's at rest to start off with, and then it's 1.2 kilograms times its velocity plus 1.8 kilograms times its velocity, which we know, 2.0 meters per second. I made it positive in this drawing, so let me put that in there. So now I solve for V final. So we've got 1.8 times 2. This is 3.6 kilograms times meters per second. I want to put the units on here just to show you what that looks like. All right, so I bring it over here, negative 3.6 kilograms times meters. Not times, I'm trying to go too fast here. Kilograms times meters per second equals 1.2 kg times V. So 3.6 divided by 1.2 is 3. 1.2 divided by 1.2 kg. Kilograms cancel. You're left with a velocity of 3 meters per second. All right. So I'll write up the, I got it off the paper there. I'll write up the rest of these solutions for this worksheet. Not going to do them now. These problems I knew were going to take longer. Shouldn't have done the whole previous worksheet, but I'm sure you did fine. Okay. I'll talk to you guys later. Hopefully these videos will help you.